For our project, we were given a strain gauge. We decided to test the deformation of a tree branch in the wind. To do this, we attached a strain gauge to the shaft of an arrow and then used hose clamps to attach that to a tree branch. We decided to use a European beech tree because they're very flexible and have smooth bark. This made it easier to get a flat connection point. The flexibility of the tree was also important because we had to make sure that the tree was less flexible than the shaft of the arrow. If this wasn't the case, we would have gotten incorrect deformation readings. Our system consists of a strain gauge attached to an arrow shaft that's secured to a tree branch. Off of that runs 2 wires to our Arduino circuit that's held inside of a 3D printed box to ensure that none of the weather gets to the electronic components. This is all then connected to a computer that's running a live MATLAB code to show us the deformation graph.
How do you make sure that a given piece of aluminum deflects more than a given piece of wood? That was exactly the problem that we faced when creating the design for our load cell here. In order to properly measure deflection of a given piece of wood, or in this case, a tree, under the certain loading conditions caused by wind, we needed to make sure that the added aluminum piece, in this case, a part of an arrow that was cut into pieces, wasn't going to overall strengthen the tree, so we needed to make sure that it was going to deflect more than an equivalent piece of wood. How do we do that? Well, the math is actually fairly simple, and we've done things like this for the class before. We could treat the tree as a roughly circular cross-section of a given average diameter, and a cantilever beam with a distributed load of wind speed acting upon it. With a little bit of help from our friend Bernoulli, we can turn that wind speed into a distributed load in terms of force per unit area. Our strain gauge 2 is a circular cross-section, as demonstrated by the incredible circle I just drew. The circular cross-section here will be treated as a simply supported beam, given the fact that it will have 2 attachment points onto the tree when properly utilized, and it will be experiencing the same distributed load. The math looks a little something like this, to those of you who have flashbacks currently to earlier homework problems that we've done in this class. We can take our tree to roughly be equal to a European beech with a given modulus of elasticity and a calculated moment of inertia based on the diameter. Then, using the distributed load and changing our length, in this case we went for the strain gauge being placed 6 feet up onto the base of a tree, we could calculate the maximum deflection at the end of the tree there. Our given piece of aluminum bar stock, in this case taken from an arrow, has the standard aluminum modulus of elasticity and a measured diameter equal to that of the diameter of the piece of aluminum that we ended up using. What then has to happen is the length of the arrow has to change. We went for about 7 inches here. As the length increases, the amount of force exerted on the arrow also increases, causing the arrow deflection to be greater. But also, at the maximum deflection that we have here, we want to make sure that our arrow doesn't deflect more than our maximum deflection, right on over here, which would cause the strain gauge to break and no longer work. An optimization equation later, and this is the result. But how do you calibrate such a system? Well, it's a bit easier than you might think. You see, all you need to do is induce a given deflection in the strain gauge, and then measure the change in voltage that it gives you. You see, what we did was we clamped the strain gauge down and placed a given amount of weight at the end of the strain gauge to induce its deflection, simulating like a cantilever beam. Then, using a dial indicator, we measured how much at the strain gauge it deflected. Translating this into voltage gave us a transfer function much like this. This is our example of using our moving average data points as opposed to our standard data points. Afterwards, you can get a transfer function that allows you to transfer the voltage to a given displacement, allowing you to turn that handy-dandy digital measurement into a usable analog.
The gauge we were given was a strain gauge, and this gauge can actually only be attached to aluminum because per the datasheet number of a CEA-06, That O6 actually means it can only be mounted to aluminum, and that was the one that the professor gave us. So we wanted to measure the deflection of a tree branch, and unfortunately we can't directly place the gauge onto the tree branch itself, onto the wood. So since the strain gauge needs to be on that aluminum, the best thing that we could think of was an aluminum arrow shaft. It has a smooth surface and pretty much a uniform thickness, making the calculations much simpler. So here's a video of us attaching the gauge to the arrow. When attaching it, we wanted to mark the gauge of where we wanted the deflection to be, and then prep the arrow, prep the gauge, and then properly place the arrow on and make sure there was no bubbles. And we were able to do this in the first try. 2 lead wires are attached to our strain gauge using a very fine point solder tip with a process called tinning, which basically coats the iron with a solder to be able to prevent any oxidation happening. It also improves the heat transfer, and it overall just makes the process of soldering much easier. So this is like a process that soldering should always be used. And then a flux is also used to clean the tip because oxidation makes the tip kind of dark, so you want to use this flux to really make it shiny and not that dark color. We also put tape around the wire to basically act as a strain relief, so that if someone were to accidentally tug on the wire and possibly rip anything out or rip any wires and the gauge falls up, it wouldn't mess up and this wouldn't happen, and it also wouldn't cause a misreading if the wire just slightly falls out.
This MATLAB script collects live data from an Arduino strain gauge setup and plots voltage and deflection in real time. For the setup and connection, the script begins by clearing MATLAB and creating an Arduino object. This opens communication so MATLAB can read analog voltages. For sampling and settings, I set how long and how fast to sample, 60 seconds total, 23 samples per second. From this, the code calculates the time between samples and the total number of samples. For pre-allocated storage, 3 arrays hold the incoming data: voltage to the A0 readings, time to timestamps, deflection to calculated strain gauge deflection. For the plot setup, we have 2 animated plots that are created when the code is ran: voltage versus time, and deflection versus time. The animated line lets the plot update continuously as data streams in. For the main data loop, for each sample, the script computes the current timestamp, reads voltage from A0, converts voltage to deflection using deflection equals 0.007 times V minus 0.0003, prints the sample values for debugging, and adds each point to the live plots. A short pause keeps the loop sampling at the correct frequency. In short, the code continuously reads voltage from the strain gauge, converts it to deflection using a calibration formula, and displays both signals in real time for the full sampling duration.
So that pretty much wraps up our Beast project. We took a simple strain gauge, mounted it onto a tree, actually got a measurable data, which was great, and it shows how the branch moved in the wind. It was a fun challenge building everything and kind of seeing how the real life application would work with this. And thanks so much for checking out the project, and we hope you enjoyed, and make sure to like and subscribe.